So welcome to our webinar, TMT, where the universe comes into focus. So this is going to be a tag team effort by Fengshuan Liu, the TMT project manager, and myself. I'm Dave Anderson, and I lead the instrument group, and I've been serving as acting project manager, project scientist at TMT for about a year. Before we begin, we are recording the session, primarily so we can share it with colleagues in other time zones who can't join us live. The previous webinar from 2 weeks ago is now linked to from the front page of tmt.org. And once this webinar is posted, I'll send around another notice to my email distribution list with the exact location of both webinar videos. Okay, so turning to today's talk, our purpose in giving this webinar is to highlight the excellent technical progress that the project is making and provide a forum for the TMT community, i.e. all of you, to ask about what's happening next and what's going on. But we're also here to remind everyone about the powerful capabilities of TMT. So feel free to ask questions in the chat, and Fengshuan and I will respond after the presentation. With that, I will start sharing the presentation and hand it over to Fengshuan.
Okay, thank you so much, Dave. And this is a tag team. I will start first. Dave Anderson is our project scientist. Next slide, please.
Okay.
So with TMT and Giant Magellan Telescope and NORLAB, we formed the US Extremely Large Telescope Program. Next slide. And TMT is the only ELT that will cover the northern skies. This enables full sky coverage. And we meet and exceed the ELT in sensitivity, speed, and performance. You'll hear more from Dave on this. And we're the only project that really benefit from the proof of design heritage by Keck observatories for over 30 years now. TMT is a public-private partnership with significant nations, some of the most strategic allies. That's next slide. That's the government of Canada, India, and Japan, together with Caltech and University of California system. And we hope the US National Science Foundation, SF, will join us for the construction. Next slide, please. So TMT's preferred site is MaunaKea. We're doing everything it can to make MaunaKea work. We do have a full backup site, the ORM in Palma, and we have full permits for both sites. Being the only ELT in the northern side, we not only enable the full sky coverage, but being at a different longitude with other two ELTs, so we also help with the time domain science. Next slide, please. And so we are addressing some of our biggest challenges. For almost a decade, our biggest challenge has been Hawaii, access to MaunaKea. And we have made significant progress, as indicated in the last webinar 2 weeks ago. And we'll continue to committed working with Native Hawaiians in the most respectful way to co-create a future that uplifts all. And this is very promising now. Our biggest challenge as of today, by far, like many of the science institutions, is a federal funding for the future potential construction funding or MREFC funding. We're working very closely with NSF, and we passed the preliminary design review, entered preliminary design phase over 2 years ago and passed the review. And for the last 2 years, we received a small amount of design development funding from NSF. This is not a commitment for future construction, but nonetheless helps a great deal to reduce the risk, and we'll report later in this talk. NSF continues to working on federal version of the environmental impact statement, including the Section 106 cultural conservation in Hawaii, and they haven't given up. They've been continuing working on this as far as we can tell. NSF director commissioned an external review of the US ELT last year, and the review report came out in December recommending both TMT and GMT to enter final design phase, citing both already. And as we speak, this week and last, we've been working with NSF to find ways to enter the final design phase so we can proceed to final design review. Meanwhile, a lot of the partners, a lot of the work are funded by our existing partners to bring the program closer to final design standard. A lot of progress is made here. Next slide. And so you look at the 8-10 meter class telescopes that were built over a course of a decade. They were not built at the same time, yet they have been after almost 30 years. They are all doing wonderful science, contributing and there's to astronomy. There's never short of enough work to do, and TMT will present 2 orders of magnitude leap forward compared to the current best. And it's important for us to arrive at the right destination, even though we won't be the first. And we're inspired to watch the awesome progress of EELT, and it does serve as inspiration for us. We just cannot keep up. We have to keep going. Next slide.
Okay.
So now I switch to Dave.
Yeah. All right. Thanks, Feng Xuan. And so in my section of this talk, I really want to focus on what an amazing, powerful tool TMT is going to be for the astronomy community. And that begins with our name, the 30-meter telescope. We have this collecting area that's much larger than any of the current optical and near-infrared telescopes. And that, of course, allows us to be more sensitive. But even more than that is that 30-meter aperture gives us the spatial resolution that we don't have with other telescopes. In particular, I think everyone knows that the diffraction limit of a telescope is inversely proportional to its diameter. And so TMT being much larger than these other telescopes, when we employ adaptive optics and can get to that diffraction limit, we can do some really amazing science. For example, we can go in our solar system and we can image moons and watch the weather on Io. We can look at nearby stars and we can start looking very close into those nearby stars to try to find planets in the habitable zone. JWST is an absolutely amazing telescope, obviously, and it's producing headlines left and right, and great news, great science, fantastic telescope. But it is only an 8-meter telescope, and so we'll have 4.5 times the spatial resolution of JWST, and this allows us to do things that are impossible to do at JWST, like follow the orbits of stars as they circle the central black hole in our galaxy to understand general relativity and massive black holes. This is something we can do at TMT that JWST can't do because it's such a crowded region. Similarly, anything that's very compact, basically unresolved with JWST, TMT has a chance to start picking apart those objects and understanding them in greater detail. But TMT isn't just about the size of the telescope. It's not just because it's a 3-meter telescope that we're excited about it. The whole design of TMT is special, and I think we have a really great design for our telescope. And this goes back to the people who came up with the idea for TMT. And one of the leaders of that, of course, was Jerry Nelson, who's the father of segmented mirror telescopes, the force behind getting the Keck telescopes built with segmented mirrors. And so after the great and rousing success of building Keck, Jerry and others got together and say, okay, what's next for astronomy? What can we do? And when they decided on where a sweet spot was of a 30-meter telescope, they said, okay, at 30 meters, we can achieve this technically, it's technically feasible, and we can have great performance, and it's also going to be great for science. And so that is the baseline for our 30-meter telescope. It's stayed, this basic design has stayed through the years. And once you start with that decision, then Jerry and the others have established a whole series of requirements on the science and on the observatory to achieve the most amazing astronomy with this telescope. So he placed demanding requirements on us, and we've worked hard over the years to make sure that the TMT that we are designing and want to build will meet those requirements in order to have the best performance. This starts with the optical design of the telescope. We have a relatively simple design enabled by being at this sweet spot of 30 meters. We have just 3 mirrors, the large 30-meter primary, a M2, and then a tertiary mirror, which steers light to different instruments on the Naismith platform. So this is a very clean design, only 3 elements. So ELT made the design decision to go larger. So they're at 39 meters. They were at 42, and then they shrunk their design to 39. So they were faced with additional challenges because they were going larger. I think one thing that they did is decide to fold their optical design of their telescope in order for it to be more compact. They also incorporated adaptive elements into their adaptive mirrors into their telescope design. And in order to have something that they could build, that turned out to be M4. And so they have a 5-element telescope design before the light gets to the instruments. So we have an advantage in that we only have those 3 mirrors, so we have a less of a hit to our total telescope reflectance, and we have lower thermal emission from our telescope. In addition, our telescope design only has a single segmented mirror, and that of course is the primary, and this makes the global alignment and figure control less challenging. Both EELT and GMT have multiple segmented mirrors working together, so they have additional challenges. Our simple, clean optical design also allows for a very high fill factor, so we're making the most of 30-meter aperture, having the largest possible collecting area. Our telescope design is compact, and our structure is too. The structure is an amazing machine put together by, or designed by Melco and NAOJ, and it will be able to move rapidly around the sky, point accurately, and also has been designed to minimize vibrations in the observatory so that we're not plagued by having residual vibrations on our diffraction-limited images. All of this telescope structure is inside an amazing dome. The Colette Dome isn't unique to TMT, but we're one of the few observatories to go with this design, but we think it really fits our telescope. Extensive modeling has shown that when wind is crossing our dome, that it will go over these kind of eyelashes around the aperture, and will be a smooth flow of air over our telescope. This minimizes the dome turbulence, ground layer turbulence. There's minimal wind shake. All of these factors will lead to an improvement in our AO performance, as you'll see. Furthermore, the TMT dome is very compact, so we're only about 20% larger than a lot of the 8 to 10 meter domes. And this is very important when we want to minimize our footprint at our primary site of MaunaKea. So as Feng Xuan mentioned, we have 2 sites. Primary site is MaunaKea, and our backup site is ORM. MaunaKea, as you can see from this selection of site characteristics, is either the premier or one of the very premier sites for telescopes in the world. It is at a higher altitude than the other ELT sites, so it has less air above it, less atmosphere above it. It has great characteristics for adaptive optics. That's these terms surrounded by the blue box. And by the way, ORM is also very good for adaptive optics. It's very good atmospheric characteristics. MaunaKea is also extremely dry, and it has the lowest nighttime temperature. Both of those things are very important for the thermal infrared. So next, I just want to mention the instruments. I am the instrument group lead, so I could, easily, spend a long time talking about that. I'm going to restrict talking to the instruments just to the single slide. Feel free to ask questions later. But what I want to point out is that our instruments are large, as one would expect for a 30-meter telescope. And they're also on these Naismith platforms. So we have 2 Naismith platforms. So if you're following the French Open, they're as large as a tennis court. If you're following the NHL playoffs, they're about the size of a hockey rink. So it gives you an idea. These are large platforms for the instruments. It can hold up to 8 instruments in the future. At first light, we have 3 science instruments and an adaptive optics system. So on the left here, we have WFOS, which is our wide field optical spectrograph. It's quite a large beast. And then on the other platform, we have Nefarious, which is our facility adaptive optics. That's the big blue box. And then it has 2 client instruments. It can feed light to either IRIS on the bottom port or MODIS on the top port. MODIS is a high spectral resolution instrument, fiber-fed spectrograph, and IRIS is a imager and integral field spectrograph on the bottom. So instead of focusing in on the instrument capabilities, I want to walk through the electromagnetic spectrum and talk about how TMT is going to perform excellently across the full optical and near infrared spectrum. And so we'll start in the blue, specifically in the near UV. And here that we've identified a lot of important science that can be done below 400 nanometers. So it's important that we try to observe here. And so this figure up in the upper right shows the reflectance of just the telescope optics. You can see that that GMT is really focusing on that blue performance. They've chosen an aluminum coating, and they have instruments at their Cassegrain, riding on their Cassegrain port. And so they have only 2 reflections and a very good blue coating over this region. Aluminum doesn't do quite as well in the near infrared. EELT is really focused on the near infrared and mid infrared performance, and so has selected a protected silver coating, very similar to what Gemini uses. But when you have 5 mirrors coated with that, the overall throughput really drops, so much so that their multi-object spectrograph Mosaic does not have advertised performance below 450 nanometers. So TMT, we're trying to kind of take that middle road, and we're using a protected silver coating, but with a near UV enhanced coating on it. And this gets us sensitivity down to 310 nanometers, the atmospheric cutoff on MaunaKea. And it doesn't sacrifice performance in the near infrared. So, so with all of that, then we can start comparing the ELTs and the relative sensitivities. And so we're looking at a couple performance metrics for multi-object spectrographs. And in this plot, we're only comparing TMT and GMT because ELT isn't working at these wavelengths. The first metric is the collecting area times throughput. That's pretty straightforward. And this would be most useful if you were observing with these instruments either using a long slit or just if you have a single object in your field. And here the collecting area of TMT and the very high throughput of the instrument really play into our advantage, as well as the excellent characteristics of our site. The extinction at MaunaKea, because it's a higher site, is less than at the lower sites. So this allows us to outperform GMT, GMAX, even though GMAX is also a very very efficient spectrograph. If we now want to consider relatively rare targets, so if you have a relatively low density targets there, in order to have a larger multiplex advantage, you want a larger field of view. So here we're combining area, throughput, and field of view. And you can see that here GMT is doing very well. They do have a larger field of view available for their multi-object spectrograph. But finally, like if you have a higher density of targets and you don't need the large field of view in order to fill up all your slits, then we consider just the area times the throughput times the multiplex advantage of your spectrograph. And here again, we have a strong advantage for TMT. If we go into the optical, now we can compare to ELT, and we're using the same performance metrics. And this is one place where the sweet spot of being at 30 meters comes into play. The WFOS on a 30-meter telescope has about the largest field and telescope size that allows you to have a purely refractive design for your multi-object spectrograph. So we have we can directly re-image the slits. So this allows us to have a very efficient design, very high throughput for WFOS. On ELT with Mosaic, they use fibers for their multi-object spectrograph, partly because they have to. They can't use a fully refractive design. So they take a throughput hit there. So we're very comparable to ELT. If you're looking at just the collecting area and throughput, our higher throughput makes up for the fact that we don't have as large a collecting area. If you look at this performance metric, area throughput times field of view, because the fiber system can be spread out over a larger field, Mosaic does win there. I just want to point out that these hashed marks are future upgrades to facilities. I'm not going to talk too much about it, but just point out that this bar that stands out for GMT is their manifest fiber system. So it takes advantage of almost the full view of the field of view of the telescope and can place fibers. So this would be a future upgrade for them. But overall, TMT and EELT are very competitive over these performance metrics. I just want to also mention another impact of going to a fiber-based system is that when you're doing science with these multi-object spectrographs on ELTs, you are often going to be looking at very faint objects, of course, and these faint objects will require very good background subtraction. And in order to achieve that good background subtraction with a fiber system, how Manifest does that is that they have a mode where they use 2 fibers per object, and they have a constant offset between all those fibers. So you have one on your target, one on a sky, and then you dither back and forth. And that allows you to do good background subtraction, but it cuts the number of available science fibers in half. Now I'm going to go in and discuss performance in the near infrared. And here, before doing that, I wanted to go back to the telescope architecture and looking at their apertures. So we have the 3 apertures here, all reflecting very different design choices. And but But these design choices in the telescope will be directly reflected in the shape of the point spread function, like an unresolved source. What is an unresolved source going to look like with each of these systems? And the more gaps you have, the larger central obscuration, the more light gets removed from the diffraction-limited core and spread out into a larger point spread function pattern. So on the top here is a perfect point spread function from the 3 ELTs. You can see the European ELT here has more bumps and wiggles than the TMT point spread function because of that larger central obscuration and the larger spiders for the central the support, and more light gets scattered out of the diffraction limited core out to larger radius because of that. So TMT has the largest fraction of its light in that core. In GMT, you can definitely see the effect of having 7 8.2 meter mirrors on a 25.4 mirror mount with the relatively large gaps. And that's, I mean, this is just the physics of what the point spread function is going to look like. Now, but we're never going to achieve these perfect point spread functions with our ELTs. Because we're on the ground, we have to have adaptive optics that work on minimizing the turbulence. And adaptive optics scientists always talk about the Strel ratio, and not everyone here might know what the Strel ratio is, but I think these figures show a good demonstration of what the Strel ratio is. The Strel ratio is a characteristic of showing how much effect the non-perfect correction of your AO system has on your point spread function. So you basically have if you take flux normalized images and you compare the peak of the point spread function to the perfect expectation, you get the Strel ratio. So we expect a Strel ratio around 70% with TMT and K-band. This is very good, and we've again, well, all these factors that we've talked about, the dome design, the site, and all of the design work that's gone into Nefarious has really backed up this performance estimate. Of course, all of the other ELTs have done a lot of work too to understand how good their performance is going to be, and I'm using those numbers here. They don't expect to have as good of performance using when they're using their laser tomography system. This is the higher sky coverage system. At the ratio in K-band between the performance isn't so great, but when you go down to J-band, the ratio of performance does become more stark. And so you can really see that we're going to have an advantage in the performance in J-band and at shorter wavelengths. And just to remind everyone that the exposure time for a background limited point source is going to be proportional to Strel squared, the inverse of Strel squared. This figure, this simulation shows a comparison of what the resolution these different telescopes are going to give based on our expectations of their AO performance. So you can see the larger field here, and if we zoom in on a small region, you can see the amazing image you would get from JWST. And you can see, specifically, you can see like the little diffraction rings around the objects here because it doesn't have to go through the atmosphere. Optical aberrations are very low for JWST, so it has very high Strel. And that allows it to look better than the Keck telescope, even though it's a slightly smaller telescope. But GMT, TMT, and ELT all have higher spatial resolution, and specifically TMT and ELT look quite sharp and quite more advanced than, a lot sharper, a higher spatial resolution than JWST. when we were looking at this, realized that this is kind of like the difference between going from a standard definition television to a 4K resolution. So a big advance by going to the ELTs. So that last simulation does not include anything about background. We weren't trying to simulate signal to noise or anything. It was really just a demonstration of the spatial resolution limits of the different telescopes. We have tried to compare the performance and how long it takes to do science with the different ELTs and in the near infrared by building a relatively simple exposure time calculator. We do incorporate all the effects of adaptive optics, loss due to diffraction, thermal effects, and sky background, how big your aperture is, and we tried to do a complete job, but put it together in a single spreadsheet so we can easily compare between the different systems. And I made certain assumptions. I assumed that all of the final instruments would have the same throughput. So I'm not trying to get into the differences between the EELT instruments and GMT instruments and TMT instruments. I'm just assuming that we basically have the same throughput, same detector characteristics for all. So with that tool, we can now start exploring different scenarios. The first is one that I call the spectroscopy scenario, even though my exposure time calculator is not set up to do spectroscopy. Instead, I'm looking at the points, the image point source, and saying, like, we want a high signal to noise going into our spectrograph. So signal to noise of 500 for an object at AB magnitude of 24. And for these IFUs, they're all going to be on axis. So the AO performance is going to be maximized for all of these systems. And then we can compare between J, H, and K band. And you can see that we're competitive, and in fact, a little bit better than ELT in all of these cases, and in particular in K band. And you might wonder why we perform better in K band. And that is because we cool our nefarious AO system. So the whole of nefarious is cooled to -30, which minimizes the thermal background contribution of this instrument. And you see that reflected in the time it takes to do science. Our next scenario is an imaging scenario over a 30 by 30 arc-second field of view. Both ELT and TMT make use of a technology called multi-conjugate adaptive optics. And this allows you to have a uniform correction over a larger field of view. For TMT, it's a 30 arc-second field of view. ELT has a mode where they optimize over a 20 arc-second field of view. I didn't sweat the details here and gave them the performance over the 20 arc-second field of view. And so in this comparison for a fainter star, AB26, and a lower signal to noise of 50, we look at how many of these fields you could look at, and you do quite well with TMT. We're very comparable in H band, so their larger aperture offsets the fact that our Stroh ratio is better. But that Stroh ratio difference becomes larger at J band, which makes the TMT performance peak up. And then in K band, again, we have the advantage of having a lower thermal background. Finally, because ELT also has a mode where they can optimize over a 50 arc-second field of view, and TMT only stops at this 30 by 30 arc-second field of view. I imagine a scenario where we observe 100 arc seconds, where now we're taking 9 pointings of TMT and only 4 pointings of ELT for the comparison. And there again, we're still very competitive with ELT over these fields. And I just wanted to mention that, through this process, we've been in touch with our colleagues at ESO and on the Morpheo team, and we've actually sent some team members over there to discuss air budgets and make sure that we agree on the performance of our different telescopes. And actually, the ESO has been working on trying to improve the performance of their system and improve the wavefront air delivered specifically over the smaller field. And so we're in contact with them and trying to help support that effort. Just one more view of the near infrared performance, just a different way of looking at it. This is looking at the detection threshold with a signal noise of 10 as a function of magnitude. And I chose H band. Again, this is where we're closest to ELT. In K or J, we will perform better. But even at this, it shows how all of the ELTs will make a tremendous step forward from our current ground-based observatories. We'll be able to go much deeper. So that's something that we're all very much looking forward to. Finally, we'll end our trip through the electromagnetic spectrum in the mid-infrared. So currently, the first light instruments on TMT do not extend into the mid-infrared, but we have plans for instruments that do, that go out all the way out into around 20 microns. And again, TMT will have advantages over the other ELTs because of our fantastic site on MaunaKea. We have again, cold temperatures compared to those other sites. So the background emission from the telescope will be less. And the fact that there's lower water vapor at MaunaKea opens up new windows in the mid-infrared and increases the transmissivity of the atmosphere in those windows. So all of those will be great advantages for mid-infrared instrumentation on TMT in the future as well. Now I realize I've done a lot of comparison here to ELT and trying to show where we're, outperforming them in certain cases. I just want to repeat what Feng Xuan said. ELT is going to be awe-inspiring, that it's being put together, and we're super excited for their progress. I just want you all to take away the fact that we're not going to be the little brother to ELT. We're going to be very competitive with ELT, and we're going to be doing some amazing science and some science that ELT is not capable of doing with TMT. And with that, I'm going to pass it back to Feng Xuan.
Thank you. This is so exciting. Thank you so much, Dave. And also at the beginning, I forgot to mention, want to thank Stan, our chair of our Science Advisory Committee, for inviting us to do this. So next slide, please. Talk about project status and recent progress. So we had a very successful PDR in February 2023. And since then, we have been doing a lot of work. And this is the list of all the reviews we've done. And on TMT, our reviews follow a very rigorous system engineering process. Everything is well documented, including conceptual design reviews, preliminary design, final design reviews, pre-ship reviews, production readiness review, acceptance review. Some of these reviews happen multiple times. In fact, just yesterday, observatories passed executive software pre-ship review. This part of the executive software is done, delivered, so well ahead of time. Next slide, please. And so 85% of the whole system are either in final design or in fabrication stage, different stages. Everything, all the major subsystems, everything shown on this page are actually design is done or in different stages of fabrication. That includes the summit facility, the US contribution, and the in-kind contribution from Canada includes the dome and the facility class nefarious multi-country AO system. Japan's in-kind contribution includes this large structure that's about 2,700 tons or so. And this contribution also includes the robots that can replace 10 segments over 10 hours during the day. So we do this every 2 weeks to minimize the loss to science. The primary mirror has 492 segments plus spares, almost 600 segments, and they are in production. 3 countries, US, Japan, and India. Next slide. And so we have polished so far 152 roundels, and Japan has delivered 60% roughly the mirror blanks, and they are working on the rest of the 40%. The dark green shows the roundels already polished, and the light greens are in process. So together they very quickly form a 22 meter or so aperture, which is by itself an ELT. Next slide, please. And the 3 countries in the 3 places also are working on machining, hex cutting, and they're making progress, slightly behind the polishing. Next slide, please. Indian government has really invested a lot on their own nickel for this national facility, India TMT optical fabrication facility. And it's a brand new facility. It has end-to-end capability from polishing to hex cutting, machining, to segment support assemblies, to mounting, to all the metrologies involved. It's really impressive. Next slide, please. And so this is what they're doing. They polished 2 roundels plus another practice roundels, 3 total, and they're ready for fabrication readiness at the end of this year for full production. And they're machining prototypes and around those. And they have produced 10 sets of the segment support assemblies with final production readiness later in this year. And together we have procured 2 sets of test equipment called SMAT to test all of these SSAs before they're delivered. One is in India, one is in our Monroe lab in California. Thank you. Next slide. And for the multi-conjugate AO system, we have 2 deformable mirrors in production at CLAS in France. On the left, it shows a base plate. In the middle, a lot of the actuator batches, blocks. On the right is assembly tooling that's being developed. Next slide. To drive these DMs, one has over 3,100 actuators, another for over 4,500 actuators. We need a lot of high voltage amplifier boards. Each can handle 96 channels, so we need a lot of these boards in the pizza boxes, and we need a lot of pizza boxes. And so the NRC team has completed the final design and the prototype reviews, and they are building prototypes. Thank you. Next slide. 2 years ago, we received from NSF first tranche of $6.5 million design development funding. We call it DD1, the first tranche. And we used it to have a contract with AMOS, work on the secondary mirror support system positioners. And the final design review is actually coming up in 10 days or 2 weeks and in Belgium. Next slide. The same team was awarded to work on the tertiary mirror support system and position. This is AMOS, and this is slightly behind the secondary mirror, and with a PDR scheduled in August. And there's significant synergy between the 2 systems by the same team. We're very happy with their progress. Next slide. And so just in the last month or so, we've signed a contract. Last year, we received a second tranche of $6.5 million design development fund we call DD2. And we use that to sign a contract just very recently with University of Arizona College of Optical Sciences. This is not the same college that's polishing GMT mirrors, but this is a unique capability and very good people to work with. We're very happy. They're working on our design for the metrology and polishing the second mirror. Next slide, please. Also funded by DD2 are the telescope alignment phasing system, APS, and the primary mirror control system, M1CS. In the DD1 funding, we've already done a lot of work in these 2 areas, and we successfully completed those tasks. And then with the second tranche of DD2 funding, they are planning for a final design review in November this year. And then the same week, a PDR for M1CS, a major subsystem there. So things are progressing well, working with JPL. Next slide. So also with DD2 funding, we're doing a lot of in-house work. The laser guide star facility has a FDR planned for end of this year, and the AO sequencer is also a PDR in October this year. On the left, it shows a relay lens final design, and in the middle is a hexapod full assembly with gimbal mount final design. On the right, it shows the acquisition sequence for nefarious with iris in the laser guide stars mode, multi-conjugate AO mode. So this is all doing very well. And this is very significant. I want to add, because a few years ago, this LGSF was supposed to be an in-kind contribution from China. Now China has left the project, and we have taken this over, and Corinne and her team have really brought this into completing the final design. Thank you. Next slide. So we have a multi-segment integration test facility in Monrovia lab with 7 segments, and these have really helped us to really work out all the integration test facility procedures, process, and reduce the risk for the actual implementation phase eventually. And here, if you haven't seen it, welcome to come to Monrovia and see it. And here we were just a couple months ago hosting some distinguished guests from Kavli Institute. Next slide. So in summary, TMT is the only ELT in Northern Hemisphere, and we benefit a lot from the Keck heritage with optimized design performance that rivals the EELT. Our team and partners continue making excellent progress and mitigating uncertainties coming from DC. And we're ready for NSF final design phase that's concluded by the NSF external review. With that, we'll repost this slide and ready for questions. Thank you.
Let's see. Now I have to find chat. So if you want to put up your hand and ask a question in person, we can unmute you or ask the question in chat and we can answer. There we go. Suresh.
Hi, thank you very much for this presentation. I was curious in terms of the science comparisons that you made where TMT is doing really well. Have you factored in the relative timelines of the project, because ELT will have first light sooner, and what impact that would have on TMT's scientific competitiveness?
Yeah, obviously ELT is coming together very quickly, and we see that it's going to be on sky soon in comparison to TMT. In the performance comparisons, no, we're not comparing that, but we're hoping that we don't come along so much behind that that we don't have. I think a lot of the instruments for ELT will be coming online at a similar time scale to the TMT instruments, given our current time scales. So I think we'll still have that same rough start time to be able to do some of this science.
Good. I'll answer Jenny's question. What do you view as the current largest technical risk? I would say that is because of the delays. The biggest concern I have is if a major vendor is going out of business or no longer interested in this, and we have to look for alternates. And that is our biggest concern. And we already have one incident. Unfortunately, we were able to find replacement, but we're watching this very closely. Thank you.
Okay. Sarah?
Yes, this is actually Stan Metchev here. We're about 15, 20 of us at Western University in Canada. Listening to the webinar, thank you. The question was, what second generation instruments on the ELT, which may be coming on during the same time as TMT is coming online, may significantly raise ELT's performance compared to TMT?
Well, I would say, so I think in terms of the near infrared performance and the adaptive optics, it's hard for them to make significant advancements. They have the dome that they have the optical design of their telescope that they have. They can improve their performance, and I expect their like planet finder instrument is going to be very good. But you know, there are certain limitations built into the design where we will remain competitive for a long time. And as I said, like some of their instruments are lagging. So even some of their first generation instruments will be coming online at a similar time to the TMT first generation instruments. They do have a capability of looking in the mid-infrared at first light. So they'll have that window open where we'll have to wait for our second gen instrument. But you know, I think to significantly improve the AO performance, that could take a lot, and I don't know that they have a roadmap to do that right now.
Okay, there's an online question. What mitigation strategies are being considered to cover the loss of funding from China? This was taken care of 2.5 years ago when we did the NSF PDR. It was a very high risk that China could not come through. So I made an executive decision that we are going to mitigate that risk by assuming NSF funding to cover everything that was assigned to China at the time. So in our funding plan, budget plan, and our request to NSF includes 100% what's needed to do what was assigned to China. Since then, it has actually, we've done better because China was going to polish a lot of the mirror segments. And now India has, in principle, agreed to take over that. So we some of these, what was assigned to China as in-kind contribution, are now reassigned to India as in-kind contribution. That lowers our cash requirements. So we're exploring such opportunities. So thank you.
Karun, I think, had the next question.
Yeah, thank you so much. Yeah, it's really very impressive, you know, so thanks for this great presentation. My question is more regarding the timeline. You know, I may have missed it during your presentation. So you have these two sites, you know, MaunaKea and La Palma. When do you decide to go? You know, what is the timeline where you will decide to go with plan B if that is the only option on the table? What would be the circumstances that let you decide to go with La Palma? And if you do decide to go with La Palma, are all the partners fully supportive of plan B, and or will there be another lag as we have to reorganize the current partnership?
Okay, that's a very good question. At PDR, we presented to NSF, and the NSF review panel endorsed this plan, which is we are a two-site observatory. Our preferred site is very much MaunaKea. We're trying everything we possibly can to make MaunaKea work. That said, we have a full backup in La Palma with all the permits in both places. And so we will make a final site decision when NSF funding, construction funding is available. And by far, because of our progress in Hawaii, I think by far the driving factor is when NSF's construction funding will be available. When that time comes, I truly believe MaunaKea will work out. And if not, we'll use the funding to build in La Palma. And so you often hear a misstatement that GMT is ready, TMT is not. That's not true, because we do have two sites, and we are ready as soon as construction funding is available. Thank you.
Right.
And that, because we presented this as NSF PDR, everything we presented there is endorsed by all our partners.
Sarah had a question, is ELT giving up shorter wavelengths permanently? I know that ELT was looking at a very similar coding to TMT, something with a near UV enhancement. I think they just made the decision because they're moving forward so rapidly to stick with something that they know works on, has been proven on Gemini and other telescopes to work well. So they're going with just a protected silver for now. It doesn't mean that in the future they couldn't when they're recoding their telescope, recode things with a near UV enhancement. But they still will have the five telescope optics, and unless they go to aluminum and sacrifice performance in the near infrared, they're going to be somewhat challenged in the near UV. I think Feng Shuan, you see Ben Mazen's question. That's for you.
Yes, I see the question is how much new funding is needed to get to first light, and how much is a funding request for NSF. That's also two good questions. And how much the funding total funding is needed. And there are two components. One is in-kind funding. One is cash funding. A lot of it comes from NSF. We're accounting on that. So in-kind funding from the government of Canada, Japan, India, thank you for their very strong support. That's all committed. And there is $1.2 billion total among the three countries that's committed as long as NSF funding comes through. For NSF portion of it, it's at the last year's NSF external review, we made the following statement that if NSF funding is limited to 1.6 billion, and that's all we need, we'll take care of everything else. Thank you.
All right. I don't see any more questions or hands up right now. If you do have any questions, feel free to reach out and contact us. We're happy to answer questions. We'll have this recording posted on the website, and we'll have a mechanism for asking questions there as well. So, but I really appreciate everyone coming today and giving us your valuable time. So thank you all.
Thank you. Thank you all. Very much appreciated. We need to stay together and keep going, making it work.